So in this chapter, we talk about sampling. Okay, so sampling is the process of converting continuous time signals to discrete time signals. And the motivation for doing this is because, in modern, technology, it's often more efficient to perform computation in the digital domain rather than in the analog domain. Okay. All right. So let's see how to do this. Okay. All right. So like I mentioned, sampling is to convert a continuous time signal to discrete time signals. Right. So for example, suppose you start out with this continuous time signal here, and to perform sampling on this signal, it means that you would be taking values of this signal at discrete time instants. Okay, and these discrete time instants are often, equally spaced by some period, let's say capital T. Right. So the key idea here is, is to take these samples from the continuous time signal and then process these discrete time samples, right? Perform processing on these discrete time samples and then convert it back to the continuous time signal whenever necessary. Okay. So for this operation to be valid, right, we should be able to, recover the original continuous time signal from the discrete time samples. Okay. But the question is, can we always do this? All right. The question is, when can this continuous time signal be actually reconstructed from its discrete time samples? Okay. So this is a question that we want to answer in this chapter. Now, from this example here, you can see that for a given set of discrete time samples, there can actually be infinite number of continuous time signals that fit to these samples. Right? For example, not only this signal here, if you consider this signal here or this signal here, right, they will all give you the same set of discrete time samples, right? So if this is the case, then given these samples, you wouldn't be able to recover what is the original continuous time signal uniquely, right? But if you compare between these different cases, you can sort of see that, if the signal does not vary too rapidly, then these samples, right, sort of just, connecting these samples or interpolating in between these samples, we can reconstruct, a signal that behaves more smoothly compared to these signals here that, fluctuates rapidly. Okay. So the basic idea is that for a continuous time signal to be reconstructed by its discrete time samples, the signal cannot vary too fast over time. And that typically corresponds to signals that are band limited. Right? The bandwidth of these, the frequency component of these signals cannot be too high, right? In order for us to recover it from these samples. Okay. So we can look at this more carefully. All right. So first of all, suppose that we start out with this signal x of t, okay? And we want to represent the sampling of this x of t by multiplying it with this impulse train p of t, okay? So if you multiply x of t with p of t, then it's like, it's like multiplying a continuous time signal with delta functions at integer multiples of capital T, okay? And the resulting signal that we get is this x sub p of t, right? So here P of t is a periodic impulse train with period capital T, which we call the sampling period. And therefore, this impulse train is called the sampling function. Okay. Right. So this x sub p of t is a convenient way to represent, a sampled signal. Okay. Now, if t is the sampling period, then we define the sampling frequency as omega s equal to 2 pi over capital T. Now, x sub p of t, right, is x of t times p of t. Right? P of t is this impulse train. Right? So x sub p of t is x of t times this impulse train. But since x of t times a delta at time t naught is just equal to the value of x of t at that time times the impulse, therefore, x of t times the summation of these impulses can be written as the summation of the impulse times the value of x of t at that time instant. Okay? So we can write x sub p of t as these, equally spaced impulses, each one scaled by the value of x at that corresponding time instant. Okay? Now you can visualize this. Right. So if the operation that we just mentioned can be visualized as follows. Okay? So first we take a signal x of t and multiply it with an impulse train p of t. Right? So suppose x of t is some continuous time signal like this, and p of t is this impulse train, right, separated by capital T. Then you would get x of p of t that would look something like this. Right? So this is also a bunch of equally spaced impulses, each one scaled by the value of x at that point. What does this look like in the frequency domain? Okay. So in the time domain, x of p of t is x of t times p of t, which is this impulse train. So by the multiplication property, if you take the Fourier transform of x of p of t, then you would get the Fourier transform of x convolved with the Fourier transform of p of t. Okay? Okay. So the Fourier transform of x of p will be equal to 1 over 2 pi, the Fourier transform of x, convolved with the Fourier transform of p, which is also an impulse train. Okay, so the Fourier transform of an impulse train is also an impulse train. Okay, so this thing here is the Fourier transform of p, and for an impulse train that is separated by capital T in the time domain, its Fourier transform is an impulse train separated by integer multiples, separated by omega s, which is 2 pi over t. Okay, so this is the sampling frequency as we mentioned before. Okay. Now the 2 pi cancels out, so I have 1 over t outside. And then whenever you convolve a signal with an impulse at time k omega s, you're essentially moving this to this center point k omega s. Okay? So convolving this with this bunch of impulses gives you a bunch of x's moved to these positions here. Right? So you can also visualize the operation here So suppose that this is the Fourier transform of our original signal x. Let's assume it's band limited to omega m. Okay. Now this x is convolved with an impulse train in the frequency domain separated by the sampling frequency omega s. Okay. So when you convolve this with an impulse train, you're basically moving this to the position of each one of these impulses. Okay. So you will have replicas of this at every integer multiple of omega s. Right? So when you convolve this with this, you will get something like this. Okay, any questions? Okay. All right. So again, this is the Fourier transform of the result of impulse sampling. Okay. So here x of p of t is the result of impulse sampling, and its Fourier transform is basically this repeated replica of the spectrum of x at every integer multiple of omega s. Okay? Scaled by this 1 over t, right here. Okay. Now this example here is when omega s is greater than 2 times the bandwidth omega m. Okay? So this example here is when omega s is greater than 2 times omega m. Okay. So when this is the case, then neighboring replicas of the spectrum would not overlap with each other, right? There's clear separation between neighboring spectrum, okay? So therefore, given this sampling output, you can actually recover the original signal x by just passing it through an ideal low-pass filter to extract this part out, okay? So you can actually reconstruct the original signal by passing it through an ideal low-pass filter, okay? Okay. So this is saying that if the bandwidth of the signal, right, if your bandwidth of your signal is sufficiently small, in fact, smaller than omega s over 2, right? When the bandwidth is less than half of the sampling frequency, then we can perfectly reconstruct the signal. Okay? But what if omega s is less than 2 over omega m? Right? Then we get this thing on the bottom. Okay? So when omega s is less than 2 omega m, then you would have overlap between adjacent replicas of the spectrum. Right? You will get something like this. And therefore, even if you impose an ideal low-pass filter here, you would not be able to recover the original spectrum. Right? Okay? And this overlapping of consecutive replicas of the spectrum is called aliasing. Okay. So if you go back to the original example here, all right, suppose this is the original signal x with bandwidth omega m. If you sample, right, fast enough, you can recover, right, you can reconstruct the original continuous time signal from these discrete time samples, okay? But if you consider signals that vary faster than omega m, right, so suppose you consider these types of signals or these types of signals that seem to vary much faster, then if you want to be able to obtain samples to reconstruct this signal, you would have to sample faster, right? That's pretty intuitive, right? If you have a signal that varies faster, you should sample faster as well, okay? And this tells you exactly how fast you should sample, okay? So if your signal has bandwidth omega m, then you should sample at least at a rate that is greater than 2 times the bandwidth, okay? So this is a very famous theorem, okay? So this is called the Nyquist sampling theorem, okay? So this says that, suppose that x of t is a band-limited signal, band-limited to omega m. So the spectrum is 0 for omega outside of omega m, okay? Then x of t is uniquely determined by its samples taken at integer multiples of capital T if the sampling frequency is greater than 2 times omega m, okay? So there's a, small technicality here, right? This should be strictly greater, okay? This should be strictly greater. So if it is not strictly greater, suppose it is equal, then these 2 points may touch each other, and sometimes that may be problematic, okay? But sometimes not, right? But just to be more cautious, right, we would want this omega s to be strictly greater than 2 times the bandwidth, right? Okay, so given these samples, we can reconstruct x of t by generating this, impulse sampled signal x of p of t and pass it through an ideal low-pass filter with a gain capital T, right, with a gain capital T to compensate for this 1 over t, okay, and a cutoff frequency omega c that can be anywhere between omega m and omega s minus m, okay? So I want a cutoff frequency omega c that is somewhere between omega m and this point, which is omega s minus omega m, okay? And this 2 omega m, right, twice the bandwidth, is what we call the Nyquist rate. Right, it specifies, a lower bound on the sampling rate that you must take in order to reconstruct the continuous time signal. Okay? Right. So this is probably one of the most interesting theorems in this class. Okay. All right. So this is a summary of the operation that we just mentioned. Okay. So you take the original signal x of t, multiply it by this impulse train to get this sampled sampled function x of p of t. Then you pass it through an ideal low-pass filter h of j omega that looks something like this. Okay, so this has gain capital T and cutoff frequency omega c that falls within, the separation between consecutive spectrum. Okay, so suppose x has Fourier transform that looks like this. When you multiply with p of t, the spectrum of this x of p of t looks like this, right? So you have this repeated every integer multiple of omega s. Okay. So if you pass this signal through an ideal low-pass filter, you get back the original. The original spectrum x. Okay. So if you pass this through h, you get this recovered signal xr, which is equal to this. Okay, but only when this is ideal. Okay, only when this is ideal. So as we mentioned previously, in practice, you cannot really realize such a perfect low-pass filter. Okay, so in practice, there may be some distortion to the recovered signal, but nonetheless, theoretically, this is possible. Okay. All right. So if this is non-ideal, then you will cause some discrepancy between x of r of t and x of t. All right. So this process of sampling and recovery is rather theoretical, but in practice, it's difficult to use this kind of operation because first of all, in practice, you can't really generate a delta function, okay? And it's very hard to realize a perfect low-pass filter, okay? So in practice, you may take some more, simplified approaches to sampling. So one approach is to sample by this so-called zero-order hold, okay? So this is very simple, okay? So suppose we want to sample this signal x of t, we just apply a circuit to sample and hold the value until the next sample, hold the value again until the next sample. And this is what you get, okay? So I sample here, I hold the value, I sample again after capital T and hold the value, sample again, hold the value, sample again, okay? Right, so suppose you sample here, you hold it for capital T. Sample again. You hold, sample again. You hold, sample again. Hold, sample again. You hold. Okay? Right. Now this this zero order hold operation can actually be written equivalently as the following, operation. So you can view this as multiplying the original signal x of t with this impulse train to get x of p of t that looks like this, right? So you have a bunch of these impulse trains, each one scaled by the corresponding value of x at that time, okay? And then you pass this through a filter with time domain impulse response that takes on this rectangular shape. Okay. Now, why do we get this signal when we pass this signal through this impulse response? Okay. So this is because whenever you pass a signal through a filter, right? You're taking the convolution between this and this, okay? So when you take the convolution between a signal and an impulse, you're basically moving this signal to the position of this impulse, okay? So you move a rectangle here, 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 each one scaled by the corresponding value at that point, okay? So this is what you get, right? You have a rectangle here, 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 each one scaled by the corresponding value at that point. Okay? Okay. All right. Now we can look at this operation in the frequency domain. Okay. So for the input signal x of t, suppose it has a spectrum that looks like this. Okay. Okay. So suppose that our original signal is band limited to omega m. All right. Now, when you multiply it with an impulse train to get this signal, we know from before that the Fourier transform of x of p of t will be equal to replicas of this spectrum at every integer multiple of omega s. Right? So it will give you something like this. All right? Okay. So let me draw it here.